So as of last class, a capacitor was made up of some conducting plates with vacuum in between. Now we're going to start thinking about the consequences of actually having some stuff in between. And what might we put in between the plates? Well, it could be any insulator. And instead of talking about insulators, I'm going to introduce a new word, and that word is dielectric. And it is in fact true that any insulator, any non-conductor, is a dielectric. And what do those words mean? What they mean is that if I have that capacitor and I slide a slab of, let's say, plastic or glass in between the plates, and let's say that that capacitor has a certain amount of charge on its two plates, and as I slide the plastic in, the amount of charge on the plates doesn't change. Then because that plastic is a dielectric, what happens is that the potential across the capacitor changes. It actually goes down. So the capacitance of the capacitor changes. It actually goes up. Way of seeing that the capacitance changes is that suppose that I have a capacitor and I'm holding its two plates at some particular voltage. Now I slide the plastic in, and what happens is that the amount of charge on the plates goes up. Now, how can this possibly be? The plastic is not a conductor. There's no electrons that are flying around through the conductor. So how can it be that sticking air or water or wood or plastic or glass between the two plates changes the macroscopic properties of the capacitor, changes its capacitance, changes the voltage if I keep the charge fixed, or changes the charge if I keep the voltage fixed? As a first step, we need to start thinking about this at the molecular level. So let's ask ourselves, what happens when I put an insulator in an electric field? Remember that between the plates of a capacitor there's an electric field. So let's ask ourselves, what happens when I take an insulator and put it in an electric field? What can change? Now, when you put a conductor in an electric field, electrons run to one side or they run to the other side. But what could happen in an insulator? The case that's easiest to think about first is a case where the insulator is something like water, where every molecule in the insulator is a little dipole. So in a water molecule, I have, let's say I'm the O and the two H's are at the ends of my fists. Then in a water molecule, what you learn in chemistry class is that the O, the oxygen, pulls the electrons a little bit off the hydrogen, and the O becomes a little bit negative, and the two H's become a little bit positive. So every water molecule is an electric dipole. On the slide, we're not going to draw water molecules. We'll draw more simple dipoles. We can ask, what happens if I have an insulator which is made in which every molecule is a dipole, and now I turn on an electric field? Well, we know the answer. When I have a dipole in an electric field, it feels a torque, and that torque tries to line it up. If the electric field is pointing this way, the dipole will try to line up this way. If the dipole starts out like this, it's going to get torqued like that. If the dipole starts out like this, it's going to get torqued like that. And so when you turn on an electric field, you line up the dipoles. And this is the molecular level answer to the question of what happens inside an insulator if I turn on an electric field. I said that every insulator is a dielectric. How can that possibly be? Because certainly it's not true that every molecule is a dipole. There are plenty of insulators that are made of molecules which are not dipoles. For example, what about carbon dioxide, CO2? The carbon's in the middle, but the oxygens are at the ends of a line like this. This is a nice symmetric molecule. It can't be a dipole. Or what about methane? Methane, the carbon's in the middle, and there's four hydrogens. Two of them are up like this. Yes. But then the other two are down like that. Think about your ball and stick model of methane in high school chemistry class. And that's a sufficiently symmetric arrangement that a methane molecule cannot be a dipole. So, and there are plenty of insulators like this, which are made of molecules that are not dipoles. Okay, so let's take an insulator like that and put it in an electric field. What happens? Well, it's not a conductor. The electrons don't all run to one side. But what happens? I've got these molecules which are initially not dipoles. I now put them in an electric field. Well, what happens is that the electric field deforms them slightly. Inside each methane molecule, the electric field will push the electrons a little bit to one side. So the electric field itself makes the methane molecules into dipoles. So even though the methane molecules weren't dipoles to start with, once I put them in an electric field, they become dipoles with a very small dipole moment. So, and then the same thing happens as with water. I've now turned my methane molecules into dipoles, and then they feel a torque which tries to align them. So there's a consequence in methane of taking methane and putting it in an electric field. As you might guess, the dielectric effect in methane is much smaller than the dielectric effect in water, because in water the dipoles are there from the start, and in methane the electric field itself makes the methane molecules into very weak dipoles. But in principle, in any insulating material, it's made of molecules, and whether or not those molecules are dipoles to start with, once you put that insulator, it could be glass, could be plastic, could be rubber, could be air, could be water, could be methane. In between the plates of a capacitor, the insulator, this insulating material feels an electric field. That electric field causes the molecules to feel a torque, which tries to line their dipoles up. And then now we have to ask, what are the consequences for the capacitor itself? And that is what we will do next.